Good afternoon and welcome to the Carolam Cymru revision sessions. Today's session is going to focus on higher tier GCSE physics and looking at the 2022 papers, looking at a bit of exam technique. It will be presented by Dr. Nettle from e-sgol Gymraeg and the session should last around 45 minutes where I'll go through as much of the question as possible. If you have any questions during the session, please use the Q&A, the question and answer section, and we'll do our best to answer any questions. So to begin, what we're going to do is look at that front page, the page you may often skip because you're trying to get straight to the content, but see why it's important to take a moment and look at what's presented on that front page that might be useful. We'll then have a quick reminder of the typical things on the equation page and how they can be used. And then we'll have a look at the full paper, see how many questions we can get through. And if not, I've attached the mark scheme towards the end so that if you watch this back, you can try and follow, pause and answer, or at the same time, you can carry on in your own time and see how you get on. So first of all, that front page, well, what do we see? What we see is obviously the total number of questions here, 6 questions. You can see the mark allocation, so which question is worth more, which question is worth less. And as you should know, for this summer, the ranked questions that have been pre-released, we know work and energy is going to account for a lot of the marks this year. Not only that, we also know that Newton's laws will be the second most ranked question, with radiation and half-life being in the middle. So just thinking about where those marks are going to come from will help us as we visualize how we answer the questions. Just as I mentioned last week, there's always information on other equipment you might need. So calculator and ruler is often encouraged. And what we always expect is you use black ink, avoid gel pens or any Tippex or correction fluids, pencils on the graphs, rulers if it's appropriate for that graph, and make sure you write everything as clearly as possible. If you run out of space, use the additional pages, but make sure you make a note that the question is continued on the additional page, and on that additional page you identify if it's 1A or 1A part I, just so it's clear when it is read and marked. Information that is vital to you is understanding where you'll find that 6-mark question, and in this paper it was in question 4 part A. So you can see it's that 6 marks from that 14 marks is allocated to the QER, that question of extended reasoning. So looking into the paper, you often see this if you're doing the double award and it's the higher tier. You can see there's a lot more equations compared to foundation, and there's a lot more SI multipliers. So you need to know how to write and convert from kilo, mega, giga, so kilograms or millimeters into meters. On the left, or the equation side, you might sometimes want to separate in your mind what units a lot of these come from. So hopefully you remember that these ones are often 6.1 based. You might find the next two are 6.2 Newton's laws based. You'll then find the next 5 here are 6.3 based. So the first 3 topics. And if you remember, the largest weighting in this summer exam from the advanced information is work and energy. So it's probably quite important that you get familiar with the use of this section here. The second most is Newton's laws. So ideally, you see the importance of this whole section. So to begin, first question, as I mentioned last week, this is question 1 on higher tier. However, it's part of the last 2 questions in the foundation tier. So we can start straight away. It's nice to see questions have the marks at the end because a lot of the time it helps you understand what you might need to possibly be doing. So we have a farm forklift truck that is stacking wooden crates of Welsh apples. Each crate of apples has a weight of 450 newtons and is 0.8 meters high. So identify the information that you have. Use an equation from page 2 to calculate work done. So if we go back to work done on page 2, what we'll find is work is equal to force times distance. So we can identify the equation and we can then look through the question. We have a weight of 400 newtons because that's the crate weight. And we also have a distance of 0.8. But as we work through the question, we need to think about it because this is a 3-mark question and 3 marks may often mean you will use an equation, you'll do some substitution of values, but that would be 2 marks. 3 marks means there is an additional step or there's an additional piece of information we have to use. So think, do our values make sense? If we take a single crate, which is shown in the diagram, it is going to be raised on top. However, please make sure it's clear that we have to raise it twice the height in order to stack it on the top, which means the crate will be raised 0.8 twice or 2 times 0.8. And if you correctly do this, you'll get an answer of 720 joules. So 3 marks, nice straightforward question. The second part of the question is state the gain in potential energy when the crate has been lifted. It's a 1-mark question and they've not used the word calculate, so state is looking for a simple answer that is related to the previous part because it's part I and part I. So think it through. The answer should be in joules. We've just worked out and we've just calculated the work done is 720 joules. And what we need to remember is if work is done to raise an object above the ground, then what we are doing, we are transferring energy. We are transferring potential energy to the object. So what we look for here is an answer of 720 joules because we demonstrate an understanding that we understand that the work done can be transferred to potential energy. So that's how much energy it gains as we transfer it up by 1.6 meters. Part 3 is now testing our understanding on this transfer of energy, and it's give a reason why the forklift truck will use more energy lifting a crate than the work done. So this is looking at understanding real life applications. So in a real life application, what we'd be looking for is something along the lines of understanding that there could be energy loss or additional work done due to friction. So friction means requires additional work to overcome that resistance to the movement, or you could have energy loss or energy transferred due to heat loss or sound. Because if you have seen these type of machines, you might be aware they can be quite loud at times. Part B is a 2-mark question, so we're looking hopefully to do a calculation. And what we have is we have a crate of apples has a weight of 450 newtons. So if we try to visualize it, we can visualize a crate when it's filled with apples. It has a weight of 450 newtons. When the crate is empty, so same crate, if the pen doesn't move too much, the same crate when empty has a mass of 12 kilograms. The question is, can we calculate the mass of the apples? So I hope by visualizing it, all we can see is the key thing is we will want to measure the difference between filled and empty, and we'll be left with the correct answer in kilograms. As this is a 2-mark question, there is a step to get into the final answer, and that is realizing that 450 newtons is not in kilograms. So to convert from newtons to kilograms is the skill we have to demonstrate first. So 450 newtons, and they even provide a nice hint in these brackets here. So on Earth, an object that has a weight of 10 newtons has a mass of 1 kilograms, so it's 10 times less. Or if 10 times less, we divide by 10 to get 45. That would be 45 kilograms. We can go back to where we were. 45 minus 12 is equal to 33. So the final answer is 33 kilograms. So this 7-mark question is something to consider. It's work and energy based, especially when this year there'll be a lot more marks based for that question. So think about how you might want to revise the work and energy content to best help you this year. Question 2 is a question to do with Jupiter and 79 moons that orbit around it. There's tables showing 4 of the moons and they have the names. So this question now, stars and planets. First question where we have to read information from the table, and it was the last question in the foundation, but it's question 2 here. So use information from table is the key thing here. So a lot of your answers should always redirect to how the table points you in the direction of correct or incorrect. So first of all, state which moon has the highest mean temperature. So what we're looking for here is an understanding of the temperature scale, and that the highest, especially when they're in the negatives, will be found as you move back up. So not when it's at as low as minus 171. We are looking to move up the scale to minus 139. That way, the correct answer is hopefully clear, and it is Callisto, because we read the column mean temperature, because the question is focused on temperature. The question asks us to state which moon, so if it's not clear, that means you have to put the name Callisto in, and please avoid writing the numbers. We don't want to write the numbers instead of the name because it asks for the name. State which moon. It doesn't say what temperature or what value is the lowest or highest. It's asking for the name of the highest temperature moon. Part 2 is a question to do with the solar system, and that as the orbit radius increases around the sun, the mean temperature of the planets generally decrease. So that is information they provide. We need to understand that if we visualize from bottom now, the sun here, we are trying to visualize that as we move away from the sun, the mean temperature decreases. So we're trying to picture this now, and we have, and hopefully we've understood this from our lessons, that as you go further out, the temperature generally decreases. Explain why the orbit radius of the moons around Jupiter does not affect their temperatures in the same way. So this question is now asking, well, if we were to focus on Jupiter, and I hope you see that I've not put every planet in order, I've just demonstrated them as they go up. The question is focusing on, well, if we look at the moons out from Jupiter, why is this not the same? So this question is getting us to understand that the heat source for planets and for the moons is from the sun. So the first thing we need to do is identify that moons are provided with heat or obtain their heat from the sun, are provided with heat from the sun. And as we think about this, we can also try to picture this concept. These moons that orbit Jupiter are roughly of a similar distance away from the sun. So our first mark is understanding it's the sun that's the source of the heat. Our second mark is understanding that the moons are a similar distance, especially if you're thinking of the scale of these objects. it is a similar distance when we're talking millions of kilometers. So moons are a similar distance from the sun. If we look at part 3 states that Peter is stating that as Callisto has the longest orbit time, it must be the largest moon. Determine whether Peter's claim is correct. So this is because it has the longest orbit time, so check, that is true. Does that mean it also is the largest moon? So this is a question to do with understanding that orbit time and size of moon is not linked. So 1 mark question, is Peter's claim correct or incorrect? So you could say Peter is false, or Peter's claim is false. And you have to justify why. So hopefully it's clear. If Peter's claim is false, you have to justify. So orbit time, I hope you understand, comes from Jupiter's here. So as the moons go out, then yes, the orbital radius, or the distance from Jupiter, will increase. But it's not to do with this. This question is the size, and the size comes from either the radius or the total distance across, which is diameter. So Peter's claim is false as, and you can point out, as Callisto doesn't have the largest diameter. So this is one way to think of it. You could answer with Ganymede has a larger diameter than Callisto, but the key thing here is you see the column diameter, which determines which one is the largest one. So hopefully I've left some space. If not, we have to do it here. Peter notices that Ganymede has an orbit time that is exactly double Europa's. Peter suggests that as the orbit time doubles, notice the bold, the orbit radius also doubles. Use only data for Ganymede and Europa to determine whether Peter's claim is true. So what we can do here now is focus on the 2 names, Ganymede, Europa. They've left space for us to work this out, so you might want to identify Ganymede and Europa, and sometimes it can be useful to just focus on the information in particular. So we are looking at orbit time, and we're also looking at orbital radius. So you might want to put time, you might want to put radius, just so we can pull out the information, because sometimes all of this might not be clear where we focus on. So we're looking at Ganymede, and we're also looking at Europa. We're looking at orbital time, and what we can do is pull out the time of 7.2 and 3.6, and the radius for Europa is 671,000, and Ganymede has 1,070,400. So now we can really avoid pulling out incorrect information. We've got the table in front of us, and what we're doing here is looking, well, if we take the orbital time of Europa and double it, doubling is the same thing as multiplying by 2, then we do indeed get 7.2. But now Peter again is suggesting this is also true for the orbital radius. So we can check, we can take our smaller value of 671,000 and we can multiply that by 2 because we can double it, and we can check that this value is 1,342,000 kilometers. So again, we can specify, is Peter's claim true or false, and hopefully you can see it's not true, so it's not true, and you can specify that the value is not double. So question 2, so far we've got 3 more marks to go, and we've achieved 5 of those marks. We can move into B part I, which is a 1 mark question, which is the tick the box. Can you please see in bold it says tick one more box? So avoid doing multiple ticks. If you have errors, you need to make it clear which ones you cross out, but ideally only place one more tick. So 2 of the statements below are correct. 1 statement has been done for you. The others is up to you. So the first statement is the astronomical unit is the mean distance that separates the sun from the Earth. The second comment is a light year is a measurement of time. And ideally, as you've been revising, you've noticed that light year is one of those ones that has the word year. However, it's a measurement of distance. So that bit is false. So we don't put anything in this box. You hopefully have learned that a light year is a measurement of distance. So any other factor of light hour would also be a distance. So if a light year is the distance that traveled by light in a single year, and we look at the next statement, what we see is a light minute is the distance, which is a valid statement, but it's the distance traveled by light in 60 seconds. We check, yes, this is minutes. It's also 60 seconds, so it is correct. So 1 tick here. That way then we don't have to look at the last statement, but we can check a light year is less or smaller than a light second, and hopefully you know the orders of seconds, minutes, hours along there. Part 2, 2 mark question. So we look to calculate, especially when they specify calculate straight away. But we have both Earth and Jupiter travel in elliptical paths around the sun. So information, hopefully remember the shape of an elliptical orbit is sometimes you describe it as that circle that's been squished, oval, or sometimes you might hear the words rugby ball shape, but the correct term we use is elliptical. As they orbit the sun, the closest distance between Jupiter and Earth is 588 million kilometers. So the closest distance along between Earth and Jupiter is 588 million. So we're looking at this number and we can see it's quite a long number, and that's the closest distance Jupiter and Earth ever reach. This is equivalent to 3.92 AUs, this astronomical unit. So the length of this line is also 3.92 astronomical units. So we've got 588 million kilometers or 3.92 astronomical units. It's the same line, it's the same distance, just different units. Can we calculate the distance in kilometers that separates the Earth and the sun? So to do that, we need to think. If we have a line that is 588 million kilometers long, and it's also 3.92 astronomical units, we've been asked to find the value of 1 AU. And the information we've got is we have a line that is 3.92 astronomical units, and we've also got the length of that. So actually, if we take this whole line and divide it by the 3.92, what we'll find is we'll find the length of one of these sections, which is equivalent to 1 astronomical unit. So we can picture it a bit more clearly by dividing 588 million by 3.92 astronomical units. And hopefully you can see correct use of the calculator. We will get 150 million kilometers, which is the value of 1 astronomical unit. So 8 marks, quite nice question with lots of different elements, calculations, reading a table and tick box. So there's a lot of different ways to obtain marks. Question 3 is on understanding of particles. There's the nuclear physics, the radiation side, and the first 3 marks come down to understanding of carbon 12, carbon 14, and that they are isotopes. So thinking about the summer, the two middle questions with the middle amount of marks are the two radiation and half-life topics. So this is one you definitely want to ensure you understand. So explain in terms of the number of particles why carbon-14 has an unstable nucleus and why carbon-12 has a stable nucleus. It's a 3-mark question. So ideally, when we're thinking of statements, we are looking at 3 separate statements that demonstrates a good understanding. We've got a comment here, unstable nucleus, so explain why something is or isn't an unstable nucleus. So first of all, you might want to say what makes an item or object unstable. So hopefully remember definition, the unstable nucleus. The unstable nucleus is due to the imbalance of protons and neutrons in the atom. So first of all, we now understand, and we've demonstrated we understand what an unstable nucleus is. Secondly, we can think about carbon. Carbon-12 has, and we can think about a set statement for carbon-14. So now we think of 3 separate statements. We've defined what makes it unstable, and then we've looked at carbon-12 and 14. So we need to identify the next bit, identify 6 and 12 and 6 and 14. So we want to say what this actually means. So carbon-12 and 14 has 6 for both of them, 6 protons. But carbon-12 has 6 neutrons, whilst carbon-14 has 8 neutrons. So as we think about how we answer this question, we've got an unstable nucleus is due to the imbalance of protons and neutrons. The carbon-12 has 6 and 6. So you could finish your sentence by stating that that means it's stable as there's a balance. Carbon-14 has 6 protons and 8 neutrons. So clearly an imbalance. Part B, 4 marks. Understand the 3 types of radiation, the gamma, alpha and beta. So we have an unstable nucleus becomes more stable following the emission of radiation. Complete the table below. 4 marks, and hopefully you see 4 separate sections. So we can now look at gamma first. The first mark is for recall of symbol. So recall the symbol looks like this. If you feel more confident, start with the symbols. You might remember that beta can be written as this, but there should be numbers. Those numbers would be 0 on the top because there's no protons or neutrons. However, on the bottom, we'd have a -1 because it's a highly charged electron. It would also be acceptable to write E and 0 -1 because they are the 2 ways you might have learned to write it. Description of gamma is that it's an electromagnetic wave. So use that knowledge to remember some other properties of the others. So alpha, you should have learned that it is a helium nucleus, absent of those electrons. There's a helium nucleus. You might want to say 2 protons, 2 neutrons because you know how to read these numbers. But the helium nucleus is a clear statement. And here for the beta particle, you identify that it's an electron, but you might have in your notes identified as a high energy. You could have identified as a fast moving, but it's a highly energetic electron. The key term here is, you know, this is an electron and this is a helium nucleus. So 7 marks in total. What we've done, we've considered, first of all, isotopes and stability. and then we've completed a table to help us identify the types of radiation. As we move to question 4, you can see this is the one that begins with the 6-mark element, just the 6-mark QER, and I'll avoid answering it fully because we did the QER session 2 weeks ago, so you can go through that to identify it, but we'll have a look at the detail or the level of information you can put into your answer. So we have question 4A. Since 2017, new bimodal electric diesel trains have been introduced to run between Swansea and London. A velocity time graph for one of these trains is shown below. And what's nice is that there are different sections already identified: A, B, C, D to E. Use information from page 2 and we can compare the distances. So that's why it's in bold, the distances travelled and accelerations for the parts of the journey labelled A, B, C, D and D, E. So this is a question that doesn't have values. So you might find this an odd question because there's no clear numbers or values. So don't feel encouraged to add numbers. Go to your page 2 to help you get started. So if we move to page 2, look to identify how these equations might be used without numbers. If you remember, it's the top 4 that come under the 6.1, that speed, distance, time topic. You should see that we have 2 equations right here. The acceleration is from the gradient of a velocity time graph, and the distance is the area under a velocity time graph. So when we go to the question to answer it, we could be thinking, right, the 2 equations we've identified and maybe pulled over to the page are these 2, acceleration and distance travelled. The question is asking for 4 different sections, and as it's a QER question, we need to structure it in a logical and a sustained line of reasoning. So you might be thinking, A, B, what type of content can you talk about in your first sentence? And you will go through it in logical steps. So in A, B, can you identify acceleration and can you identify distance? So hopefully you will see acceleration will be 0 as the gradient is 0. So 0 acceleration, and you will start with a nice sentence ordered there. So you could say that from A to B, the train has 0 acceleration because the gradient of velocity time graph is 0 in that section. You will say the distance traveled from A to B can be found by calculating the area underneath. And then you could comment on B, C. What type of things can you say from B to C? You can say from B to C, is there an acceleration? But hopefully you can see that it's going from a high to a low velocity. So you would identify a negative acceleration or a deceleration. And again, even though there are no numbers, there's nothing stopping you from commenting on how much that gradient is. You could say it decreases by 4 squares across in 1. So even though we don't have the numbers, you can think about commenting, but it's not necessary because you're just trying to comment on the shape of the graph. What we can do then is look at CD. After we've looked at the area here, hopefully is clear that it's again 4 squares, but it has a gap of a half, a gap of 1, but because it's the area of a triangle, you can actually work out it's equivalent to 2 squares of area. So again, there's no numbers, but there's nothing stopping you from identifying these values. We have CD. Hopefully it's clear that there's 0 gradient and there's also 0 area because there's 0 area under the graph, so 0 distance. That leaves us with dE, which hopefully demonstrates an acceleration. That acceleration is positive, and it takes 4 squares to increase in a gap of 2 time interval. The reason I'm pointing these two out is because you can compare. So you can say the rate of deceleration from B to C is greater than D to E because it changes its velocity by the same value. So 4 down, but then 4 up, but it does it in a shorter time from B to C than it does in D to E. So the rate of acceleration is greater than. And the final bit is area of DE would be 4 increase, takes 2, and again it's the area of a triangle, which is a half, so it is equivalent to 4 blocks. So we can say that the total area would be 4, 4, and 2, which would be 8. But hopefully what you should see is we have structured it, but we've not answered it. So again, remember this QER success, we have to think about what we do before we put that pen to paper. So now we have a clear structure, clear distinct paragraphs where you comment on each interval, and you could finish with the total area. That 6-mark question moves into the rest of the 14 marks, which is the first one, single mark, but there's a lot of information to get through initially. Those information is the diagram shows a 5-carriage train, so 5 separate carriages. The table below shows information about 2 types, a 5-carriage and a 9-carriage. And there's a lot of information. We can see mass, speed, the standard acceleration and deceleration, and also the standard deceleration and the emergency one. So a lot of information. For the journey from Swansea to London, 2 of the 5 carriage trains are joined, making a 10-carriage train. The 10-carriage train has the same speed and acceleration as the 5-carriage, but hopefully you notice that that's the same for the 9. State Newton's second law as an equation. So you might be thinking what you can do here. If you remember it, that's great. If you don't, maybe go back to page 2. So hopefully if I go back a few pages, check the area where you know Newton's laws appears, which is 6.2, and hopefully you identify the correct equation. So now you can come back and insert F equals ma. You can write it out in words that the resultant force is mass times acceleration, or either will be acceptable. What we now have is a clear identified equation. Part 2, use information from the table to answer these questions. Use an equation from page 2 to calculate the force needed to accelerate the 10-carriage train. So what we have here is 10-carriage train is 2 of these 5 carriages. So hopefully you recall that. So it's 2 of these 5-carriage trains. We look in the 5-carriage train information, and what we are attempting to do is calculate force. So we need mass times acceleration. So the mass is 2.3, but correct reading of the table will identify the times 10 to the power of 5. Correct reading of the question will see that it's a 10-carriage train. So there will be 2 times 2.3 times 10 to the 5, because you have 2 of these 5-carriage trains, and the acceleration, or the standard acceleration, should be seen as a value of 0.7 because you read the standard acceleration, and the resultant force should come out to a value of 322 times 10 to the 3, which is acceptable to place in here. 322 times 10 to the 3. You can convert it into full newtons of 322,000. You could write it as in meganewtons, giganewtons, but be familiar with this notation. Second part of the question asks us to use the equation which they provide to calculate the time taken to accelerate the 10 carriage train from rest to its maximum speed. So we already have the acceleration. We have an understanding of the maximum speed of 55.8. We're unaware of the starting speed, but maybe if we use a bit of knowledge that trains start from rest, you might see that the change in velocity, would be 55.8 minus 0. So this is one of the ones that often comes up because it's demonstrating that you understand it's starting from rest. The time is the only unknown, so what we attempt to do is rearrange for time. We will be left with a question of change in velocity, which is 55.8 divided by the acceleration of 0.7, and the time should come out to a value of 79.7 seconds. So we're looking at 79.7 seconds. The final part of this question is a student states that the 9 carriage train is approximately double the mass of the 5 carriage train, and if they're both traveling at the same speed, it will approximately double the time to stop in an emergency. Explain whether the 2 claims by the student are correct. So first of all, the first claim is that the 9 carriage is double the mass of the 5, and that the same speed will take double the time. So we can address the first statement. If we double the mass, what actually happens? So use the information in the table. So 2 times 2.3 times 10 to the 5 should equal 4.6 times 10 to the 5. And what we see here is 4.6 times 10 to the 5 kilograms is not identically equal to the value of 4.4, but you could comment that they are similar. So the first thing is they are similar. Now we want to think about what factors affect the deceleration. So hopefully you identify the deceleration that we just calculated, that time came from the change in velocity, that velocity, which we knew was 55.8 for the 2 of them, divided by the acceleration. So in that case, it was accelerating from start to the max speed. It would be the same the other way around. So hopefully you can see for the second statement, if the maximum speed is the same and the maximum deceleration are the same in an emergency or even standard, then hopefully it's clear that you can say the time to stop would be the same. So the time to stop would be the same. It would not be double. It would be the same as the deceleration is also the same as the deceleration is equal values. And that is a 14-mark question we've just looked at. So if we check how far we've gotten through, we've spent 45 minutes. We've reached question 5. So overall, you have question 5 and 6 to get through. I've placed the mark scheme at the back so you can look at it. And ideally, that puts you in a good place. We have 2 questions left. If you're trying to pace yourselves, you're looking at that mark a minute, means you have enough time to look through the rest of the questions to check for any silly mistakes that you don't often do, or just to check if you have fully explained questions.